So we are looking at MidTool today. Mid-training data synthesis for agentic tool use. This is a paper out of the University of Washington, Snowflake, and UNC. Welcome to AI paper slot, by the way.
Yeah.
But the core insight here is that we've essentially been teaching LLMs how to use tools completely wrong.
Yeah, we really have.
Right. We've been bottlenecking all of this learning into the post-training stages. So, supervised fine-tuning and reinforcement learning on these heavily curated traces. But MidTool proves that if you shift general tool use learning back to the mid-training stage, using this massive 20.3 billion token mixed corpus, you get wildly better agentic-based models.
Oh, absolutely.
Yeah, so by mid-training Qwen 3.4b and 8b based models on this corpus before they even touch standard SFT and RL, the researchers saw this massive, greater than 10-point jump on BFCL multi-turn evaluations.
Which is huge.
It is huge. And it even improves optimization efficiency. So your SFT converges faster and your RL adapts quicker. So our mission for this deep dive is to unpack the architecture of that 20.3 billion token MidTool-Mix, detail their two-branch synthesis pipeline, which uses some proprietary models like GPT-5, and figure out why this fundamentally shifts how ML engineers should allocate their compute.
Yeah, the shift away from post-training dependency is, well, it's essentially a structural correction in how we impart prior knowledge to the weights. Because right now, if an ML engineer wants to build an agent, they rely so heavily on SFT and RL to teach function calling. And if you think about the cognitive load we're demanding in that final stage, it's kind of absurd.
Right.
We're forcing a base model to simultaneously learn tool recognition, schema grounding, parameter extraction, and multi-step execution topologies, plus how to recover from missing information.
All the very last minute.
All of the last minute, yes. And often on these highly curated, artificially clean JSON traces that don't look like reality.
Which is exactly why the current paradigm is so fragile in production, right? I mean, when you do post-training on clean agent traces, it's kind of like trying to learn a foreign language solely by reading transcripts of people chatting in a coffee shop.
Oh, that's a good way to put it.
Yeah, you might perfectly memorize how to order a latte, which maps to your, single-turn function call.
Yeah.
But you haven't actually studied the grammar books or the vocabulary dictionaries or the cultural context that dictates how the language flows in a totally unpredictable environment.
Exactly.
And that deep structural foundation is what mid-training is supposed to build.
Yeah.
But the problem historically has been that the real knowledge needed for robust tool use, the sprawling developer docs, the unstructured API specs, messy GitHub repos, that stuff rarely exists in a format that looks anything like a clean agent demonstration.
Right. And what's fascinating here is that the field already knows targeted mid-training works. We've seen it successfully deployed for reasoning-intensive domains. Math and coding are the big ones. The domino baseline is a prime example of mid-training injecting structural reasoning priors, but general tool use presents this distinctly hostile data environment.
Hostile how? Just messy.
Highly heterogeneous, you're trying to fuse unstructured natural language documentation with executable code patterns, and then you have to tie both of those to highly rigid, structured JSON schemas. It requires a capability surface that is far, far broader than just learning Python syntax.
Right. So if the data distribution is that hostile and fragmented, the immediate question for me is where exactly did they find 20.3 billion tokens of it?
Yeah, that's the big question.
And how do they balance it? So they architected this mixture from 4 distinct source families, and they're purposefully trading off breadth and structure here. So the largest slice, 42%, is web data extracted from FineWeb. So this gives you API references, CLI tutorials, troubleshooting forums. Then you have 26% code data. And they didn't just dump all of GitHub into the pipeline.
Yeah.
Right?
Yeah, no, you can't do that.
Right. They applied aggressive heuristic filtering to isolate high-quality MCP-related repos, specifically model context protocol implementations, and they targeted the documentation directories within those repos. Then, and this one surprised me a bit, 23% is PDF data from FineBDFs.
Oh, yeah.
Because this is where you find long-form product handbooks and hardware manuals. And it has a ton of extraction noise, obviously, but it's really dense with crucial procedural knowledge.
Procedural content, exactly.
Right. And then finally, the remaining 9% is strict tool data, so native APIs and MCP skills.
And that ratio is very deliberate. The web and PDF slices, they construct the broad technical context, the semantic understanding of what a tool does and the conceptual workflow. Then the code repositories inject the executable syntax and the error handling patterns. And finally, those structured tool artifacts, that 9%, that provides the strict formatting guardrails. You really need the complete spectrum to build a robust underlying prior for software interaction.
Okay, but I have to push back here. Because if they're scraping all this agentic web and code data, a large-scale scrape of GitHub and web tutorials immediately sets off data contamination alarms.
Oh, for sure.
I mean, if you're pulling down thousands of repos full of tool use examples and API docs, aren't they just accidentally training on the evaluation benchmarks and cheating the results?
Well, the researchers were hyper aware of that risk. They implemented a very stringent exclusion pipeline. So during the GitHub crawl, they actively maintained a strict blacklist of benchmark repositories. They filtered out anything related to BFCL, Talbench, MCP-Universe, basically any agentic evaluation suite before pre-processing even started.
Yeah, but a repo-level blacklist only prevents the most obvious leakage. What happens when a developer copy-pastes a BFCL benchmark snippet into a random web tutorial? Or it ends up in a PDF presentation somewhere? A blacklist isn't going to catch semantic leakage or, fragmented anagram overlaps scattered across the web slice.
Precisely why the blacklist was only the first layer of defense. They ran a rigorous post-hoc contamination analysis using decon across the entire synthesized mixture, and to ensure they caught those fragmented snippets, they tuned the decon ingram token length threshold aggressively low.
Like how low?
They shifted the window down to catch the 13-gram matches. Yeah, rather than the standard 50-gram block matching. So they scanned the web and PDF slices, plus all the synthesized trajectories, against the evaluation sets of BFCL v3, Talbench, and MCP-Universe.
But wait, if you lower the anagram threshold that aggressively, down to 13, you are bound to generate massive amounts of false positives just from standard API syntax, right? Like boilerplate code. Did Deacon actually flag genuine leakage?
It flagged fewer than 20 candidate overlaps in total.
Really? Out of 20 billion tokens?
Yeah, and all of them were isolated to the web slice matched against BFCL. And when the team manually inspected these candidates to determine if there was actual semantic leakage, meaning the model was exposed to actual reference answers or benchmark logic, they found every single one was a false positive.
Oh, wow.
Yeah, they were just generic API documentation pages that happened to share surface-level n-grams with a benchmark item, like standard REST boilerplate. There were 0 actual benchmark instances or reference answers in the data, so the MidTool-Mix is completely clean.
Okay, so establishing that the performance gains are uncontaminated allows us to actually dig into the synthesis architecture. Because having 20.3 billion tokens of raw PDFs and GitHub markdowns is, well, it was practically useless on its own.
Right.
You can't just feed a raw 50-page router manual to a base model and expect it to learn how to execute a multi-turn REST API call. So the core contribution here is how they synthesize that unstructured data into high-signal training trajectories. And they engineered this 2-branch synthesis pipeline designed specifically to target the 2 primary failure modes of agentic behavior, which are grounding and execution.
Let's start with branch 1, the context-grounded trajectory augmentation. This directly attacks the grounding deficit. They deployed Qwen 3.235b as the teacher model to process those messy web pages, PDFs, and code. And the objective here is affordance extraction.
Meaning the model isn't just extracting a basic API endpoint. It's dynamically mapping the boundary conditions, the expected parameter types, prerequisite workflows, and it's pulling all of this directly from unstructured markdown.
Exactly. The 235b model reads the noisy text and structures it into a strict capability profile. Once that profile is mapped, they use a rule-based planner to allocate a specific generation budget to create QA pairs and multi-turn chains that are grounded exclusively in that document's context.
Okay.
So this teaches the base model how to infer missing parameters and navigate ambiguous boundaries purely from unstructured text, which mimics exactly what an agent has to do when it gets deployed into a new software environment in the wild.
Right. So branch 1 handles the grounding, teaching the model how to parse the environment, understand what the software expects. Branch 2, native agentic trajectory synthesis, targets the execution side. So they take the explicitly structured APIs and MCP skills, that 9% of the mixture we mentioned earlier, and they synthesize fully executable, verifiable trajectories. And for this branch, they utilize teacher models with massive context windows and advanced reasoning capabilities, specifically the GPT-5 family.
Yeah, GPT-5, 5.1, and 5.2. And generating native trajectories requires strict constraints, because if you simply prompt a teacher model to generate tool use traces, the probability distribution heavily favors overproducing trivial single-turn calls. They're just computationally easy to generate.
And take the lazy road.
Exactly. To counteract this, the researchers implemented a deterministic budget controller. This controller actively constrains the sampling space through rigorous temperature scaling and logic bias manipulation. It essentially forces the teacher model into edge case generation, demanding complex, multi-turn behaviors where information is intentionally missing.
So the agent have to execute clarification calls before proceeding.
Exactly.
Okay, so they're using structural constraints to force the teacher model out of its lazy generation habits, guaranteeing the resulting data teaches multi-step planning rather than just reactive API firing. Furthermore, they augmented this branch with rollout trajectories from Agentic world models, AWM, and integrated filtered nemotron agentic data to ensure robust compositional behaviors. And the necessity of having both of these branches is just laid bare in the ablation studies.
The ablation results demonstrate a perfect division of labor within the model's weights. The native trajectories from branch 2 are the engine for precise function calling. They drive the massive performance spikes on syntax-heavy benchmarks like BFCL. Conversely, the context-grounded data from branch 1 is the architecture that enables transferability to entirely unseen tools.
Oh, so that's why it does well on the real-world stuff.
Yes. That grounding data is what allows the model to score highly on TalBench and MCP-Universe. Remove either branch, and the comprehensive agentic prior just collapses.
Right. And that theoretical architecture translates to staggering empirical gains when they applied it to the Qwen 3, 4B, and 8B base models. Looking at BFCL v3, which stringently tests function calling accuracy and syntax formatting, the 4B model mid-trained on MidTool-Mix, followed by standard SFT and RL, demonstrated a massive leap in multi-turn capabilities.
Let's hear the numbers.
It jumped from an SFT-only baseline of 43.75% to 58.48%. Yeah, we are looking at nearly a 15-point increase specifically on the multi-turn, missing parameter, and long context subsets. That definitively proves the model has internalized multi-step planning rather than just memorizing JSON formatting.
And when we transition from static syntax evaluations to interactive real-world execution, the delta becomes even more pronounced. On TalBench, which evaluates interactive task completion in complex verticals like airline reservations and retail database management, the MidTool-Mix fundamentally altered the model's reliability. It nearly doubled the overall pass at 1 rates for the 4B model compared to the baseline.
Doubled?
Nearly doubled, yes. And we observed identical trends on MCP-Universe, which tracks execution success over live MCP servers for browser automation and financial APIs.
Okay, while the benchmark top lines are impressive, the most critical takeaway for the ML engineers listening, the people actually tuning these pipelines, is the optimization efficiency. Because mid-training fundamentally reconfigures the loss landscape for the downstream post-training phases.
It really does.
Analyzing the SFT loss trajectories reveals that models initialized with the MidTool-Mix begin with a significantly lower loss value. And the gradient descent is much steeper and faster than both raw-based models and those mid-trained on generic datasets like Domino. You are burning a fraction of the GPU hours to reach convergence.
And the RL phase is where the structural advantages of mid-training truly compound, particularly when applying GRPO or group relative policy optimization. When you initialize GRPO on a mid-trained model, the starting policy distribution, the pi theta, is already aligned much closer to the optimal agentic policy.
Right.
Because of this proximity, the model starts from a substantially higher reward state. But more importantly, it incurs far fewer KL divergence penalties when measured against its reference model during exploration. It adapts rapidly in the early steps of training.
A standard-based model will eventually adapt during GRPO, though. Like if you throw enough compute at it, the reward curve for the non-mid-trained model will climb until it reaches a similar plateau within that specific training environment.
Yes, but that is the trap many teams fall into. In-environment reward convergence is merely a proxy for adaptation to the training set. It is not a guarantee of generalized capability.
Right, the overfitting problem.
Exactly. The base models brute force their way to a high reward by memorizing the narrow paths of the training environment. But because the mid-trained models possess that deep structural prior we talked about, they vastly outperform the base models on out-of-environment downstream tasks. The mid-training provides robust generalizability that survives contact with novel APIs, whereas the base model's RL policy is brittle outside its training distribution.
And an RL policy collapsing outside its distribution brings us perfectly to the capability boundaries mapped out in this research. Because honestly, analyzing where a model fails is often more illuminating than where it succeeds.
Oh, absolutely.
So on MCP-Universe, despite the massive gains across nearly every category, the score for web search remained anchored at a flat 0.00.
Which defines the precise perimeter of what a general tool use prior can accomplish. Mid-training excels at teaching general schemas, extracting parameters from context, composing basic sequential workflows. However, web search within the MCP-Universe framework is a fundamentally different class of problem.
It's open-ended.
It requires deep, exploratory, open-ended reasoning. The agent must formulate a query, parse dense HTML results, identify missing information, refine the query, and iterate over a long horizon.
Right. Teaching a model to flawlessly execute a structured REST API via Swagger files does not magically endow it with the long horizon reasoning required to synthesize information across multiple divergent search queries. It highlights that exploratory web search requires its own dedicated trajectory synthesis and highly specialized reward modeling. But while they found a hard boundary on web search, here's where it gets really interesting. They inadvertently triggered a massive capability overhang in the visual domain.
This was wild. The visual tool pilot study is easily the most profound finding regarding representation learning in this paper. They took a multimodal base model, specifically Gemma 3.4 BPT, and mid-trained it exclusively on the text-only MidTool-Mix.
Exclusively text.
No images, no visual trajectories, no bounding box coordinates. After fine-tuning, they evaluated it on Visual Tool Bench, and the text-only mid-training caused the Visual Tool success rate to jump from 0.58 to 0.72.
That's crazy. A model gets 14 points better at manipulating visual tools without ever seeing a visual tool during its mid-training phase.
It's incredible.
But to understand why that happens, we really have to look at how Visual Tool Bench actually functions. A huge percentage of successful visual tool use relies on the model-generating environment-oriented code to invoke those tools, like writing a Python script to crop an image based on coordinates, or orchestrating a pipeline to pass an image to an OCR model.
Exactly. It's a transfer of structural orchestration. Because the MidTool-Mix is heavily saturated with complex CLI operations and executable code patterns, the model internalized a highly robust prior for software engineering and environment orchestration. Think of it like learning the deep spatial physics in a high-fidelity driving simulator and then realizing those exact same spatial and mathematical priors make you significantly better at flying a drone.
Wow, yeah.
The medium changed from text to vision, but the underlying mathematical logic of how to orchestrate software remained identical. The text-based structural knowledge transferred directly to the multimodal space.
Text-only mid-training, teaching a model the physics of visual tool orchestration, is just an incredible insight into how these weights actually learn. So to distill all of this for your own training pipelines, relying on post-training SFT and RL on a few thousand curated JSON traces is a dead end for building resilient agents. You have to build the structural foundation during mid-training. You need the unstructured documentation, the GitHub repositories, and that dual-brain synthesis to teach both context grounding and precise execution.
The empirical evidence is definitive. Modifying the base model's priors through mid-training creates a highly favorable optimization landscape for downstream RL. It drastically reduces compute costs and is the necessary prerequisite for achieving true out-of-distribution agentic reliability.
We want to leave you with one final thought regarding the trajectory of this technique. Right now, executing the mid-tool pipeline requires massive proprietary frontier models. The researchers had to deploy Quinn 3.235B for affordance extraction and the GPT-5 family for the complex execution trajectories. But open-weight models are advancing exponentially. We are rapidly approaching the compute threshold where a mid-tier open-weight model will possess enough innate reasoning to run its own mid-tool pipeline.
Now that is an interesting thought.
Imagine a deployment ecosystem where an open-weight model autonomously ingests the messy, unstructured documentation for a brand new proprietary software stack, synthesizes its own QA pairs and multi-turn execution trajectories, and dynamically updates its own tool use priors through continuous mid-training. We are looking at the foundation for an autonomous, self-improving agentic loop that requires zero human data curation and zero reliance on frontier model API calls. The implications for the decentralization of agentic compute are staggering. We will leave you to explore the math on that one.